Hi there, my name is Shayan Shiran, and I'm a deep learning and AI enthusiast. So, and today I'm going to talk about convolutional neural networks. But before I but before I mention the table of contents, I'd like to say a quote from Jeff Bezos, and that quote is: "Be stubborn on vision, but flexible on details." I'm more than happy to present this topic to you, and I am one of the members of Hoopad's R&D department. Today, I'm going to talk about the history behind neural networks. I'm going to give a brief but concise history of neural networks, and then I'm going to talk about CNNs and their components. And then I'm going to talk about the main purpose of these series of presentations, and that's going to be distributing CNN over edge constrained devices. So let's go and begin the history. Uh, let's go back to 1940s, and to be precise, in 1943, neuropsychologist Warren McCulloch, the man you're seeing here, and mathematician Walter Pitts. They were inspired by how the brain neurons work, so they connected some electrical circuits together to simulate intelligent behavior. This was the first, and they have a neuron, I will mention it in a bit later, called McCulloch-Pitts neuron. Uh, and this was the first attempt on neural networks. In 1949, psychologist Donald Hebb published a book named The Organization of Behavior. In that book, he proposed that neural pathways strengthen over its successive use, especially between neurons that tend to fire at the same time, thus beginning the long journey towards quantifying the complex processes of the brain. So, uh, in the 1950s, to be more exact, 1954, the first Hebbian network was successfully implemented in MIT. Uh, According to what Donald Hebb proposed, that I mentioned in the previous uh, slide, he actually believed that neurons that fire together, they tend to learn more. Uh, and then in 1958, psychologist Frank Rosenblatt, he is also known as the father of AI, he proposed an idea named Mark I perceptron. You're seeing Frank Rosenblatt here in the picture, and this is Mark I. This is Mark I perceptron. Uh, there is a history behind Mark I perceptron. Frank Rosenblatt was working on simpler decision systems, like the ones present in the eye of a fly, right here. Uh, uh, these uh, uh, these simpler decision systems, like the one present in the eye of a fly, determine these kind of creatures' flea responses. So, in an attempt to understand and quantify this process, he proposed the idea of a perceptron in 1958, calling it Mark I perceptron. So, Mark I perceptron uh, was a really simple input-output relationship that was modeled on a Macaulay-Pitts neuron that I mentioned earlier. A Macaulay-Pitts neuron takes in inputs and takes a weighted sum and returns zero if the result is below our threshold and one otherwise. But it had one drawback, and that drawback was it couldn't perform XOR operations. So, in 1959, Bernard Widrow and Markian Hoff developed the first neural network successfully applied to a real world problem. These systems were named Adeline and Madeline after their use of multiple adaptive linear elements, uh, which I think Madeline was specifically designed to element noise in phone lines, and it is still in use today. Uh, and let's go to 1960s. In 1969, Marvin Minsky and Seymour Papert published a book named Perceptron. They argued that Rosenblatt's single perception approach to neural networks couldn't be translated effectively into multi-layered neural networks. And it was after these comments and conversations and these interviews that investing establishments uh, took a step back and didn't invest in neural networks. And it was in that time that the AI winter began, and it was for nearly a decade. I believe it was between nearly 10 to 12 years. And there weren't any special work in the field of neural networks uh, until 1982. John Hopfield presented his paper on what came to be known as Hopfield net, and it was around these years. I believe it was in 1980, maybe in 1987. Uh, Japan started a committee that they are going to use neural networks in a huge scale, and then United States began to use the same thing. In 1985, Paul Verbus, the man you're seeing here, saw the potential in backward propagation. It was a new thing back then. He saw the potential in backpropagation and the way it can help neural network, but his work wasn't noticed until Parker noticed his work, and it was years later where other scientists like Rumelhart, Jeffrey Hinton, and Williams formed the very first neural networks. And that was the brief history of neural networks. The next part of my presentation is about CNNs, and we start by its definition. What is CNN? In machine learning, a classifier assigns a class label to a data point. For example, an image classifier produces a class label. For example, we have a picture, and our classifier labels the things that it sees in the picture. For example, it sees a bird, it labels it, it's a bird. I don't know, it sees a bag lots of other lots of other things. Something like YOLO. We are seeing that something that we are seeing in YOLO is like it's a type of a classifier that labels the things that it has detected. A convolutional neural network, or CNN for short, is a type of classifier which excels at solving this problem. And you can see in the picture it has some components, and I will get to these components in a bit later. Uh, there is neural networks have some training phases to complete, and their training phase involves two steps: forward propagation and backward propagation. In forward propagation, the input data is received, it is processed, and the output is generated. In backward propagation, we calculate the errors and update the parameters of the network. But we are not going to talk about the training of CNN because our main purpose is the inference we get from distributed CNNs. There are two parts that CNNs usually have. Almost each CNN has these parts. It's the input data, the convolutional layers, and fully connected layers, and the output. The convolutional layers are the layers that extract features from the input, and the fully connected layers uh, use the data that was generated by the convolutional layers to generate the output. Uh, and let's go one by one for these, and let's talk about these components one by one. Uh, the first component is the input layer. The input layer represents the input image into the CNN. And thanks to CNN Explainer, it's a website that you can see how CNN works. Uh, they have visualized uh, CNN in a great format that I think it's really fun to learn. The input image, uh, the input layer represents the input image into the CNN because we use RGB images as input. The input layer has three channels corresponding to red, green, and blue channels, as you can see here in the picture. And then we have the convolutional layers. The convolutional layers are the foundation of CNN, as they contain the learned kernels or weights, we can say. They are the ones that extract the features that distinguish different images from one another. And this is actually what we want for classifications. And as you can see here in the picture, we have some kernels. Each channel has a unique kernel for itself. Uh, and let's see what a kernel is. A kernel is nothing but a filter. It is used to extract features from the images. This kernel moves over the input, and performs a dot product with the subregion of the input. It depends on the size of the kernel.
سر تو گوشی باشم نمیفهم به قرآن که خودش موافقم Please everyone, listen. از اول آیه تاریخی در مورد هوش مصنوعی رو بعد سال 1960 شروع کرد آقا
Guys, it's recording. Come on. It's recording.
کلابه
All right. The, as I said, the kernel moves moves over the input data, performs a dot product with the subregion of the input. It depends on the kernel size and the stride. Uh, stride is the we can say is the pixels to be shifted. For example, and I cannot show it here, but I think I have it here. Yeah. And you see the input here has a padding. I will get to padding later. These zeros that you are seeing here, these are paddings. I will talk about paddings in a short while. Uh, Kernel size is an important hyperparameter. Usually there is a difference between small kernel sizes and large kernel sizes. They say that small kernel sizes extract much more information. But the larger ones, they extract less information. They are usually good for larger sets they are usually suitable for larger sets. but but it usually depends on your type of work. So, but most of the time, having small kernel sizes is much more better because you get uh, better information. You extract much more information from the input layer. As you can see here, I put a picture here to fully understand the differences between small kernel sizes and large kernel sizes. As you can see here, uh, this top figure has a kernel of size 2, and its stride is 1. Let me let me see if I can draw something here. Uh, Forget it. I cannot draw anything on here. I don't know how to draw a thing here. You see, for example, the stride is 1 and our kernel size is 2. First, the kernel moves over this region uh, of our input, and then it shifts 1 pixel at a time because our stride is 1. And then it performs a dot product here, and then the output and the result is stored in this particular index. So, and as you can see, as you can see here, the kernel size is now 4, and we can see that the extracted features are much larger than the one in the above figure. Let's
Excuse me, strike by default small.
By default it's 1, but yeah, we can set it different. We can set it 2, for example. Yes, it's a hyperparameter. You can set it, but usually it's 1. It's the default one. You can set it to 2, and I don't know if we can set it into more pixels or not. I think I haven't seen any. But if you have seen any, just tell me. I don't know. Have you seen any? Strides more than 2. We have strides more than 2. We have strides more than 2.
Yes, we have strike more than two. Yes.
All right.
For picture more bigger pictures. Picture size is big.
So you mean when the pictures
Another picture. When we have get another we can use stride mode.
where what?
When we have a high resolution.
We have when we have a high resolution pixels, we can use more than 2. All right. And padding. You see, padding is often necessary when ker- when the kernel extends beyond the activation map. Padding conserves data at the borders of the activation maps, which leads to a better performance and can help preserve the input's spatial size. I think one of the main reasons for padding is that it preserves the input's spatial size, uh, and it will also allow an architecture designer to build deeper and higher performing networks. Uh, as you can see, there's a
I have question. We always do this padding because I saw in networks we have size is going to be small in next layers, and I think they don't do padding in next layers. Padding is the same and size is going to be
size is going to be smaller.
yes, and they don't do padding because padding saying is the network automatically understand which dimension the next layer should have and append padding to the previous layer.
According to what Yasin said, he says uh, the layers can tell how much padding
It will need to
it will
for the
need
next
for the next layers.
have
So if
same
it
dimension.
needs any padding, it will add the padding.
we do padding, the output size of image is same as input, I think. It's true. And when we do this, the size is still same in all the layers.
Is he right? Does the size still the same? Is it still the same?
We have two ways to set the padding. You can do explicitly manual by, for example, we have zero padding,
We have
one
different kinds of
padding,
techniques, yeah.
average padding.
The most common padding is zero. Zero padding because it's simple. They say it's simple and it performs well.
Some padding using regression and get average or some numbers, mm, average. regression
Go on.
کردیم اینکه
Sorry.
تقریبا این چیزی که ما داریم شبیه هم با اینا میشه یه فقط صفر نزنیم سیاه بزنیم. Yeah, there are different kinds of ways. One of them is to extend the new.
All right. Any other information that you can provide?
Parameters same, you set the output size of image, output size of that layer to be the same size as the input size of next layer. And when we do this, the output size is going to be small, and the next layer is small.
You say that layer by layer, the size is going to get smaller.
Yes, it's going to be.
And this is the formula behind the convolutional layers. This formula was mentioned um, in the paper Deeper Things. Deeper Things is a framework used for distributed CNN, and they usually use cross correlation for it. For convolutional layers, they use cross correlation. And you can see the formula here, and you can see the cross correlations formula here. And I will go on to the next slide. And we have some activation functions in neural networks and CNNs. We have different kinds of activation functions, and one of them is RELO. Uh, and you see, today neural networks are tremendously accurate because they add a non-linearity function to it, and these non-linearity functions are the activation functions. Uh, and they add this non-linear activation function because convolution itself is linear. So they do not want the output to be linear. They add a non-linear function to it. And Relo applies much needed nonlinearity into the model. And as I said, nonlinearity is necessary to produce nonlinear decision boundaries so that the output cannot be written as a linear combination of the inputs. And you can see here in the picture, Relo activation function is rather simple. If it has uh, you can see here it just it just chooses a max between two numbers here. You can see it's 0 and 0.13, so it chooses 0.13 because it's much more bigger. That's a simple activation function. And then we have these layers called pooling layers. Uh, Pooling layers have a main purpose, and their main purpose is to gradually decrease the spatial content, the spatial extent of the network. As Mushtaba said, as you can see here, the input size is 60 and 60, and the output is going to be 30 and 30.
I forgot, but cooling layers are for smalling the size and do this.
They gradually decrease the special content. Uh,
Cooling, installing, padding, large video. And you know,
yeah.
yeah,
And these pooling layers reduce the computation, the overall computation of the network. And then again, we have different kinds of poolings. One of them is max pooling. We can use max pooling for our pooling layers, and we can have thousands of these layers. I mean, we can have we can have thousands of convolutional layers, we can have thousands of pooling layers, and and today's state of the art CNNs usually have uh, a lot of these layers. And the next and one of the next layers is the flatten layer. Uh, this layer converts a three-dimensional layer in the network into a one-dimensional layer. Uh, Having a flattened layer is necessary because uh, because we want to specify which class, uh, for example, which class we have, which type of class we have. So we flatten the outputs, for example, here, a pooling layer into a one-dimensional layer, a one vector, actually. For example, here we have a 13 by 13 by 10 uh, layer, and then we will have one vector which its size is 1690, and here I produced I put another example. I didn't put the one here in the picture, and as I said, it's essential for making the for generating the output, and we have to use the flatten layer because we need it. And we have another activation function named softmax that acts again as a non-linear function, and we use the softmax function to get the probabilities of data points. Again, we can use some other activation functions that are similar to softmax. And you can see here in the example how it works. And here is its formula. It's simple, and I'm going to go to the next part. And this is the math behind the fully connected layers. Uh, it's somehow like the formula of convolutional layers, but this one doesn't have any cross correlations. And let's go to the main purpose of these presentation, and it's about distributed inference. Uh, for fully connected layers and convolutional layers, the number of weights stored in the weight matrix and the weight tensor dominate the memory requirements. And hence, we approximate the memory footprint F subscript n. It's better for us to pronounce it FN. We Persians use it. We can call it FN. No, I'm not. I'm going to say it FN because it's more easy for me to pronounce it than saying F subscript n. So FN is the number of weights stored in the weight matrix, and it just sums the number of the weights, as you can see here in the formula. T here is the longest execution path. It's the number of parallelized multiplications, the multiplications that we had. So, but here they are parallelized, and we have a communication overhead that is denoted with C. If we perform our CNN, if we get the inference on a single device, our communication overhead is zero. But the communication overhead is the uh, what can we say? It's uh, the number of input. As you can, let me just mention the example. You see, here we have some layers. These are the inputs and the outputs of these layers. If you want to understand what communication overhead is, uh, we have the communication overhead in this figure is zero because there are no other devices. But in the below figure, we have two devices that they are in series. They are not in parallel. The other device, we talked about this on our way out with Yasin yesterday. Uh, there's an approach for this. We can use it. We can use them in series, but we can use. But the uh, core purpose is to use them in parallel. Here, the communication overhead is 16. It's the number of inputs and outputs exchanged between the layers and the devices here. It's between the devices. Here is 16. We can have we can have different communication overheads. And this 16 is just an estimate. Uh, and the communication overhead actually uh, depends on the inference runtime. It's really important. The inference runtime, and you can the number of we can calculate the number of weights here, and it's, for example, 4 times 8 plus 8 times 16 plus 16 times 4 plus 4 times 4, and this is how the uh, weights are calculated, and we can get the memory footprint. And actually,
Mr. Shiran,
yeah,
N is the number of devices, or
yes, here n is the number of devices,
L is number of
is the number of the layers.
layers.
Layers, yes.
In here, L is for overhead, it is 16.
The overhead in this figure is 16.
So what is L now? L is 16.
L? No,
Is L
no.
16?
Here we have two devices, right?
But
We have two devices. We are going to have, and the communication overhead is 16. You see? Let me see. No, it doesn't have. Because the devices here are in series, we just get you see here there is a partition here. You can see a partition here. If the partition was, for example, placed here, our communication overhead would have been 4.
so we have 16 layers that the outputs are
No,
in
no, not 16 layers. Our the output size is 16.
the output size is
For
16.
example, we have 16 neurons, we can say.
Uh,
They're
That
the size of it, not the layers. These are the layers. The layers are denoted as L.
that feeding to the next size.
Yes, they are fed. Yes, they are fed to the next layers. They're the input and output sizes. The numbers that you see here are the input and output sizes of the layers.
So what is the L in the formula? It's number of layer or
Yes, it's the number of the layer.
layers?
The layers, yes. You see,
Okay.
here for L1, it's 4 times 8. For example, for the memory footprint, it's 4 times 8. This is for one layer. Then the second layer is 8 point times 16. And then we sum these together to get the memory footprint. Yeah.
And go on. If net is disconnect, the output of layer saved in database or not, it's gone. Thinking of the
Yeah, he's, he's actually thinking. You see,
other device.
he's actually asking a pretty much important question that they have not mentioned in their papers. You see, I have read the authorized paper thoroughly. They just explain the framework, but they do not tell how these devices are connected to each other. Yeah, so I don't know if it if it disconnect if the devices are not connected. I don't know what happens. If yeah, if,
And another question, the devices have to be connected in series or
in
parallel?
this example they are in series,
There's
but
sequential.
but the but the core approach is to be in parallel. The devices should be in parallel.
And F is standing for device 1 and T is standing for device 2. Yes?
No, no,
No?
no, no,
Wait, we have
no,
to.
no. T. No, no. You see, Michelle, T is the number of parallelized multiplications. We have, see, this dot product here is the multiplication. All right?
Yes.
The number of parallelized multiplication is denoted with T. In all of these examples, the number of parallelized uh, multiplications, it's going to be the longest path, the longest execution path in the CNN is equal to F. In all of the examples that I will mention, they are all equal to each other. I mean, F subscript N and T, they are equal to each other.
Thank you.
You're welcome. You see, F is the number of weights stored. It's the number of weights. It's how much memory we need. We can say that. It's the memory footprint. It's an estimation of how much memory we need here. Uh, for for the purpose of distributing CNN over edge constrained devices, they have proposed some methods. Yes.
What can we do? What can we do to better this paper and we write other paper? We have done. So write
Huh.
paper, let him explain the rest. We still don't know how does it work.
Yeah, that's actually the main thing. We don't know how it completely works. We don't know. You see, I did mention how the formulas work, how we can, and I will mention how we can partition the layers. But how they are partitioned, we don't have anything on it. You see, they didn't publish any codes.
Connect the flash.
You see, we have frameworks, as I said, Autodice and deeper things. These are I can say these are the best for now. For these frameworks, One of them was implemented 5 years ago. Deeper Things, yes, Deeper Things was, uh, I believe it was written in C or C++. plus plus. It was written in C. The framework was written in C, and Autodice was, again, I don't know. It was whether C or C++. plus plus. They actually have talked about how their framework works, but they didn't mention how their devices is connected and how they have achieved. Yeah, they have just explained how their framework works. They didn't say anything further about it. You see, they have implemented. You see, they have. Yes, we can. Yes, we can have. We can use our own ideas to implement uh, this kind of CNN. You see, in the papers they have reached a framework. They said what the framework does, but and they have evaluated the results on it. We can see we can see the results in their papers. I don't know. They have reached 38%. They have used 38% less memory than other types of CNNs, especially state-of-the-art CNNs. I don't know. They have achieved uh, more than, I don't know. For example, 15% in speed. Yeah, it got fat. It can be faster, but it depends on the uh, GPUs and the CPUs that the edge devices have. They in their papers they usually use Raspberry and maybe some Jetson Nanos, but they do not use any. Yeah.
CNN is same as when we use multi GPUs for training the network. Are they the same things? When we use multi GPUs, we distributed the calculation over the GPUs. Are they the
Are the
same
GPUs in a single device?
in single process? Like
No,
they are
that's not distributed CNN.
it's not
Distributed CNN is across different devices.
different devices using internet, like internet or
Yeah, something like that. They have to use a communication protocol.
in one location or other locations.
They can be in other locations. It's not necessary to be in one particular location.
And
That's
this
that's
is the
that's the
advantage.
how question. I don't know how they are connected to each other.
No, no. And this is the advantage of distributed CNN when you use.
Yeah, you see, the computation load is not on one device. The computation load is not on one device. The computation is distributed evenly in different devices. Guys, you're not talking about training. Training is a different. We have a different. We have a different approach for training. This is just for inference. I I believe I said it in the beginning of my presentation or in the middle of it that this is just for the inference. We are distributing the inference over edge devices. We are not training it. No, no, no. We are not training it.
For inference, we don't need a huge device or huge
We,
hardware.
we can use.
For training, we use
There's for training that we use.
we can use edge for example, just detect car, some car. And another device we detect color of the car, and the other device we detect any faces of in the car. Yes. What are talking about is, for example, two different kind of models that are running on different devices. But this presentation is not, for example, what we have one model, and for example, three layers of model.
Okay. You see,
In the
no,
last
no, no.
device,
You
we
see,
finally get
you
our prediction. It's
yeah,
better like
you
this.
see, we get what we want eventually, but you said something. It's different. You said that one of them detects the car, and then the other one detects the color. No,
I say wrong.
no. You see that that's not the case. Uh, it just detects a car,
Yes, yes,
nothing else.
yes.
Detecting a car is distributed over different devices. Different devices are running in parallel. Different devices are running in parallel to detect a car, for example.
This model run in different model any device or different devices distributed.
We can run different models on different devices.
This presentation about
But
running a model
yes, this
one model
presentation is running
over
about
different devices. Gustavo, this
one model in on
one model have a 100 layer. I understood that what you said, but you said different. Correct.
he does he understood he understood.
You laughing? Laughing. And
You see, there's here for the partitioning part. So how do we partition the layers into different devices? They have proposed some layer partitioning methods, and they have categorized them into two different kinds. One of them is partitioning the feature dominated layers, which are usually the early layers uh, in a network. We can say the convolutional layers. And the other one is partitioning the weight dominated layers, which are usually the last layers in our uh, neural networks, the fully connected layers. They are the weight dominated layers. Here, for partitioning the feature dominated layers, the same authors uh, wrote another paper which they proposed a state of the art method which is called fused tile partitioning, FTP. Uh, an FTP usually puts usually stacks and puts the layers information, as you can see here in the picture, in an n times n grid, and then it uses these tiles. It puts them in tiles and then it uses them. And I don't know a lot about these fused tile partitioning, and I think it's going to be for later presentations so that I can uh, read what it is. I don't know anything about it much. I don't know anything much about it, so I'm going to address these uh, method in my next presentation. Uh, let's talk about partitioning the weight-dominated layers. Uh, they have proposed three uh, three types of methods for these for partitioning the weight-dominated layers. Uh, One of them is layer output partitioning, one of them is layer input partitioning, and the other one is fused layer partitioning, or we can say fuse. And this is how layer output partitioning works. Again, f subscript n is the memory, fn is the memory footprint. T again is the number of parallelized multiplications, which are, as I said, they are usually the same. And the communication overhead is calculated with a different formula, as you can see here. I will get to the example and you will see how it works. Um, Here, the output is partitioned into uh, the output is partitioned. As you can see here, we have the layer one here in the picture. Layer one, partition one, can be run on device one, and layer one, partition two, can be run on another device. Can be run on device two. But you see here we have all the input neurons. These A here, denoted A, is our input size. We have the input neurons in both of our devices. We have them in both of our partitions. And then for each partition, we sum them up together with the weights. We perform the mathematical operations that I mentioned earlier. And then we use the activation function. And at last, we produce a subset of the outputs, which is B denoted L here. Again, on device 2, the same thing happens, and then we produce another subset of the output neurons, and then they are concatenated together.
So two networks should be the same as each other, or they can be different.
The network, you mean the neural network, right? They should be.
Architectures.
They should be. The neural network architecture should be the same.
So maybe they learn same thing and they produce the same output.
We are using different weights here. We're not using the same weights in the you see in partition one we are using a subset of the weights, a different subset of the weights. In partition two we are using another subset of the weights. They may overlap, but they are usually different subsets. They are not the same
What is the advantage
weights.
of concatenating the output of two networks?
These are the partitions so that we can reach the overall inputs. If we do not concat the partitions, we are not going to have the layers output. You see here it doesn't perform any special thing. The concatenation is just putting them back in a.
I mean, we have uh, two networks which are somehow
We haven't.
similar in.
We have a network which is partitioned into two parts.
We have a network, or we
It,
have two networks which are equal.
we are using a single network. You see, it's a you said it's we have for
You said they both have the same architecture.
yes, they have the same architecture.
So separately, which of networks can, for example, inference, for example, can do for inference?
You mean one of these partitions?
Yes.
Are they able to
Yes. Exactly.
have the inference? Uh, I'm not sure if each of these partitions specifically, for example, layer one's first partition can do the inference, but I think they must be concatenated to produce the inference, because we produce a subset of the outputs, not all of them. We need all of the outputs to get the inference result that we need.
Why don't we use separately and feed it to the neurons? And I think this is doing this. This doing this.
This is doing what?
Separately feeding to the neurons.
Feeding what to the neurons?
Output of devices. Layer output.
You mean
Then
here?
layer. Yes, here.
It's concatenating the outputs. It's putting them together. You see, this is all layer one. The picture you're seeing here, it's what's happening in layer one, just layer one. But you see, we can say that we have a single device, a single device that we can call it, for example, a server. The concatenation is going to be performed in the server. You see, one device, we set a device to be, for example, our server. It's not a server. I'm just saying it. It's just a word. I just want to say how it works. The concatenation is done in one device.
We're concatenating output of devices in one device.
Yes. We're bringing them back into a device.
And the concatenated outputs will feed in.
Will be fed to another layer, to the next layer.
So.
And then again, we can have another layer output partitioning. It doesn't matter. We can have all of them. You see here, in this example here, we have two devices, and we can calculate the communication overhead with this formula. But this is a rather, it seems like a difficult equation, but it's not. I will get to it in a short while, but the communication overhead, we can calculate it like this. The communication overhead is the number of the arrows that are invading these partitions. So here the communication overhead is 4 plus 4 plus 4 plus 8 plus 8 plus 2 plus 2 and again plus 2. That's our communication overhead here. But again, the memory footprint, as we mentioned, F and T are the same. For example, and we can calculate them here. It's the same as the previous examples, as I mentioned here. All right. Never give up. All right. Let's continue our presentation. The other method for partitioning the weight-dominated layers is layer input partitioning. In the previous slides, we partitioned the outputs Here we partition the inputs. Uh, as you can see here, LIP takes a partition subset of A to calculate a respective partial output of B. B is our output neurons and A is the input neurons. Uh, and here I've mentioned that while we are now using a different subset of weights, and the number of weights required per device remains unchanged compared to LOP. I mean, the F subscript, and the memory footprint stays the same in both methods. In both LIP and LOP, F here is the same. And T is also the same. Just the communication overhead changes uh, in LIP, and you can see its formula. It's here, uh, where we can say that M is the input size and K is our output size, and N is the number of devices. Here we can calculate the communication overhead for this example also. We can calculate it and then we can get the results. We have another partitioning method, which is fused layer partitioning, or we can say fuse. Uh, in fuse partitioning method, it combines both LOP and LIP together. And by combining them, uh, a synchronization point is eliminated, and thus it gets a bit faster. Infused layer partitioning, you can see it in the picture. It has uh, here is LOP, the first one is LOP, and again, for example, in this intermediate layer is LIP, and then again it merges and concatenates the weights that it gets, and then applies the activation function. But here we have to have two consecutive layers. The layers should be continuous. We have to have, for example, layer 1 and layer 2. We can have fused layer partitioning for two consecutive layers. We cannot perform fuse, for example, for layer 1 and layer 3. We have to apply it to two consecutive layers. For example, layer 1, layer 2, layer, so for example, layer 3, layer 4 is together. They are together. And fused layer partitioning also has an example. In fused layer partitioning, the communication overhead is calculated by the formulas you see. We have two fusions in the previous picture. We have two fusions here, so we are going to have two formulas for each of the fusions. But if data reuse, if we are not enabling the data reuse, fuse 1 is actually the communication overhead for fuse 1 is 0, and then we calculate for the fuse 2. And you can see the formula here, and again it's just the sum of the numbers and the arrows that are crossing the device boundaries. It's 4 plus 16 plus 16 plus 4. It's simple. It's how it's calculated. It's simple, but yet again, the implementation of it is pretty much hard. And that's it for today. Thank you for listening to my presentation.